Alright, folks. The last type of counting we did was the addition principle. So you could think of it as counting disjoint sets. You could think of it as counting with the word or. But this lecture, we're going to talk about counting independent events where you have different sets. You can think of it also as multiplying with the word and. You'll see what I mean in a second. So the big principle for this is, let's say we have n different sets. We'll call them A1 all the way to AN. Well, if we want to count how many elements are in the Cartesian product of all these sets together, well, all we need to do is determine how many elements in each set and multiply that together. So that's going to be your principle that we're going to use throughout these next few examples. So let me give you an example of what I'm talking about. So, how many different license plates are there? That are of the form just like a Manitoba plate: letter, 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 number, number, number. So, our solution to this, well, if L is the set of all letters, then the size of L, well, there's 26 letters, A through Z. And the numbers are really digits, right? So how many digits are there? There's 0 through 9. That's 10 digits. So we need a choice for each of the 3 letters and then each of the 3 numbers. So basically, we're looking for the size of L times L times L. That gives us all the different combinations of 3 letters we can pick. And then times N times N times N. That's all the combinations of the 3 numbers we can pick. But we know the size of each set, so it's just multiplying everything together. 26 times 26 times 26 times 10 times 10 times 10, which I guess you could write as 26 cubed times 10 cubed. So this is kind of the standard example. Let's do just one more, maybe even one more that's a little bit easier. So you have, let's say, 7 pairs of socks and 3 pairs of shoes. Oh, let's put some pants in there as well. So make this a comma, and then let's say 4 pairs of pants. How many different choices for your clothing do you have? Well, we need to choose a pair of socks, and we need a choice of shoes, and we need a choice of pants. So we have 7 choices for the number of socks, and we have 3 choices for the number of shoes. So just with socks and shoes, there's 21 different combinations of those. And then I have 4 pairs of pants. So this is 7 times 3 times 4, which is 84 clothing choices. Let's do one more, in fact. Let's do example 42.4. Let's do this one. How many 4-digit numbers contain exactly 1, 2? So, for this one, well, 4-digit numbers, I'm going to say can't start with a 0 as well. Because if a 4-digit number starts with a 0, then it's not really a 4-digit number. We'd never write it like that. So our 4-digit numbers, well, we'll have 4 digits in there. So our question is, where can the 2 go? Well, there's 4 different places for the 2 to go. It can go in our first spot, or it can go in the second spot. Let me write down a few of these, or here, so it can go in the second spot, it can go in the third spot, and it can go in the fourth spot. So, my next question is, well, how many choices do I have for the rest of my digits? Well, there's 10 digits, but I'm not allowed to pick 2 anymore here. I can pick the digits 0 through 9, doesn't matter which one, as long as it's not a 2. So, let's put the number of choices in red. So there are 9 choices for a second digit. Again, it doesn't matter what I choose here. It doesn't affect what the third digit could be. So it'll be 9 choices here. And similarly, 9 choices there. So if my number starts with the 2, there's 9 times 9 times 9, which is 81 times 9, which is 729 different numbers that look like that have exactly 1, 2. Or, well, the same logic applies for the 1's digit and the 10's digit. I can choose 0 through 9. There's 10 digits, but I'm not allowed to choose 2 because my number needs to have exactly 1, 2. So there's 9 choices for the 1's digit. Similarly, 9 choices for the 10's digit. But for the 1000th digit now, remember, it can't start with a 0. So I only have 8 choices for my 1000th digit. 1 through 9, but not 2. So not 0 or 2. And then that's going to be, well, that's going to be 8 times 9 squared, which is, what is that? That's 628, I believe. Is it? No, 648, sorry. In fact, let me just check that over the side here. Yeah, 648. Okay, great. And similarly, well, same logic is going to apply to the other 2 cases. 9 choices for the 1's digit, 9 choices for the 100's digit, but only 8 choices for the 1000's digit because it can't be 2 or 0. And then, same thing here, 8, 9, and 9. And again, this is going to be 648, 648. So, well, it can look like the first model in 729 ways, or it could look like the second model in 648 ways, or the third model in 648 ways, or the fourth model in 648 ways. So the number in total, and I do want to note that every way here, So all of these are disjoint. There's no overlap, so we can just use the addition principle that we talked about last class. So we add this up, and we get 3 carrier 3, 17, so carrier 1. So that's what, 26. So there's 2,673 different numbers that have, 4-digit numbers that have exactly 1